You ever stop and wonder what you have in common with, say, a blade of grass? Well, the answer is pretty much everything. Today, we're going to dive into the incredible journey of energy and matter, a story that kicks off with the sun, flows through every single living thing, and yeah, it ends right back with us.
So let's start with a little riddle. How does a sunbeam become a beetle? It sounds kind of impossible, right? But I promise you, by the end of this, you'll see it's just pure, amazing science at work.
Okay, so our journey starts with the ultimate power source for nearly all life on our planet, the sun. It's literally the engine that drives the whole shebang.
Now, the secret to tapping into all that solar power is a process I'm sure you've heard of, photosynthesis. This is that magical moment where plants take pure light and turn it into chemical energy. In other words, they make their own food.
Let's break down how it works. A leaf soaks up sunlight, pulls water up through its roots, and breathes in carbon dioxide, or CO2, right out of the air. It then mixes all that together and creates two super important things: sugars, which are its fuel, and the oxygen that we all need to breathe.
So yeah, you can honestly think of it just like a recipe. The ingredients: sunlight, water, and CO2. The kitchen where all the cooking happens, that's inside these tiny things called chloroplasts. And the final dish? You get delicious sugars for the plant with a side of fresh oxygen for the rest of us. Pretty good deal, huh?
All right, so our plant has turned sunlight into energy-packed, tasty leaves. So what happens next? Well, that energy is about to get passed on. And to see how, we need to zoom out and look at the whole ecosystem.
So, in pretty much any ecosystem, you've got two main players. First, you have the producers. These are our plants, making their own food. And then you've got the consumers, the eaters, who get their energy by, well, eating other organisms.
And this right here is why we call it a food web, not a simple food chain. It's way more complex. Look at this desert scene, for example. The cactus gets eaten by a squirrel. That squirrel might then get eaten by a snake, which could then become lunch for a hawk. It's this huge, tangled network of energy just flowing from one life form to the next.
But here's where the story gets really interesting. This transfer of energy from one organism to another, it's not a perfect handoff. In fact, there's a really strict rule that governs the whole process.
So let's go back to our hawk and snake for a second. When that hawk eats the snake, does it get to absorb all the energy from every single mouse and lizard that snake ate in its entire life? The answer is a big fat no, not even close.
And here's why. We can visualize this with what's called an energy pyramid. Each step up this pyramid is a trophic level. You'll notice at the bottom, the producers have 100% of the energy from the sun. But watch what happens as we go up. The available energy just plummets with every single step.
And here it is, the key number, just 10%. On average, only about 10% of the energy from one level actually makes it to the level above it. That's the rule. That means a whopping 90% of the energy is lost at every single stage of the food web.
So where in the world does all that other 90% go? Well, it gets used for all the stuff that life requires. You know, moving around, growing bigger, making babies, and a huge chunk of it is just lost as body heat, radiating away into the environment.
So, we've established that energy makes a one-way trip through an ecosystem. It flows in and then it flows out. But the physical stuff, the atoms that actually make up every organism, that is a completely different story. Unlike energy, matter isn't lost. It gets recycled.
The easiest way to think about it is like this. Energy flows. It comes into the system as sunlight, moves through it, and eventually leaves as heat. But matter cycles. The actual atoms of carbon, nitrogen, and water are used over and over and over again in a never-ending loop.
And if you want the perfect example of this, look no further than the carbon cycle. This is basically the planet's grand recycling program for carbon, an element that is absolutely 100% essential for all life as we know it. Carbon's journey is just fascinating. It goes from the atmosphere into a plant. Then an animal comes along and eats that plant. When that animal breathes out, or when it eventually decomposes, that very same carbon goes right back to the atmosphere or the soil, ready to start the whole cycle all over again. It's a constant dance between the living and non-living world.
Now, for millennia, these cycles have maintained this incredible, delicate balance. But in a very, very short amount of time, a new factor has entered the equation with enough power to really throw things off. And that factor is us.
Here's the core issue. By burning fossil fuels, coal, oil, natural gas, we're basically digging up ancient carbon that was locked away underground for millions of years. and we're pumping it into the atmosphere as CO2 way, way faster than the planet's natural systems, like plants and oceans, can absorb it.
And this imbalance has some really profound consequences. One of the biggest is something called ocean acidification. See, our oceans are amazing. They act like a giant sponge, soaking up about a quarter of all that extra CO2. But here's the catch. When CO2 dissolves in water, it forms an acid, and that starts to change the ocean's fundamental chemistry.
This image says it all, really. On the left, you see the ocean of the past, with a chemistry that allowed all sorts of life to thrive. But on the right, that's the projection for our future. It's a more acidic ocean, where the very building blocks for things like shells and skeletons become hard to find. And that threatens entire marine food webs, from the tiniest plankton all the way to the top.
Which brings us right to our final thought. Energy flows, but matter cycles. It just keeps going, forever. The very atoms that make up our world today are going to be a part of the world of tomorrow and the day after that. So the question we're left with is this: what is our responsibility for the kind and the amount of atoms we choose to put back into that timeless system?